How do you perform surgery on a single molecule when your scalpel is jagged, random, and essentially invisible? This is the fundamental paradox of atomic fabrication. We cannot build perfectly if we cannot see the tools we are using. Traditional scanning tunneling microscopy, or STM, relies on metal tips that are atomically jagged and unpredictable. Because the tip's shape is random, it often creates distorted images and makes reproducible interactions with surface atoms nearly impossible. This randomness blocks the path to mechanosynthesis, which is the use of mechanical force to drive chemical reactions. To build nanomachines atom by atom, you need to know exactly which atom on your probe is touching the surface, something standard tips cannot allow. To solve this, the researchers completely inverted the paradigm. Instead of using an unknown tip to image a surface, they use a known molecule on the surface to image the tip, effectively turning the microscope upside down. The method relies on two precise components, a flat crystalline silicon probe chip, and a rigid molecule called EAOGE-C2I. This molecule stands upright like a tripod, acting as a fixed scanner that looks back up at the probe. When the probe scans over this molecular tripod, the result is a reflected probe image. This technique allows the researchers to clearly see the individual silicon dimers, pairs of atoms, on the apex of the probe itself. Once they can see the probe structure, they align the molecule with a specific hydrogen atom on the probe's surface. By physically lowering the probe, they mechanically pluck that hydrogen atom off, using zero voltage. The reliability of this mechanical method is stunning. In 28 controlled trials at cryogenic temperatures, the researchers successfully removed the targeted atom 27 times, achieving a 96% success rate. Theoretical calculations using density functional theory confirm why this works. The data shows that as the probe gets closer, the energy barrier for the reaction vanishes, making the transfer of the hydrogen atom thermodynamically inevitable. While powerful, this technique is demanding. Creating the atomically clean silicon probes requires heating them to 1,200 degrees Celsius in an ultra-high vacuum, alongside precise management of the probe's tilt. This breakthrough opens the door to actually writing with atoms. By creating dangling bonds on the probe, we can create atomic memory bits, or anchor points for building complex, covalently bonded 3D nanostructures. To learn more, head to emergentmind.com.